Welcome to Maths with EJD. In this video, I'll be talking about linear programming versus non-linear programming. Definitely, this whole series is about linear programming. So, but there might be cases where linear programming breaks down, and that is why we want to see this comparison to know how far linear programming can go. So, of course, we already know the abbreviations. LP and NLP, that is linear programming and non-linear programming, are they are fundamental, two fundamental approaches in mathematical optimization. In mathematical optimization, used used to find optimal solutions to a variety of decision-making problems. Okay. Now, first of all, let's consider linear programming. I guess I want to call it code at this point. So let's look at LP. So linear programming involves models where both objective function, where both objective function and all the constraints are linear functions. In these models, variables appear in a straightforward in a straightforward um proportional relationship proportional relationship with no powers, no products, or other or other non-linear operations or other non-linear operations involved. So we don't have all these non-linear operations involved. Okay. So linear programming is often used in scenarios where relationships are approximately linear. Relationships are approximately linear, and it is particularly it is particularly well suited well suited for problems well suited for problems that are relatively simple to analyze and solve. Okay. Of course, we've seen several examples of linear programming, right? But let's just refresh our minds about this. So let's look at an example, of linear programming. So consider a manufacturing company. Consider a manufacturing company that produces consider a manufacturing company that produces two products, A and B, with limited resources, e.g., labor and materials. So, of course, we don't always have sufficient supply of these things. So that's why there are constraints. So we now suppose, if we suppose that each unit, each unit, each unit of A requires 3 hours, 3 hours of labor and 2 units of material. Okay. And then each unit of B, each unit of B requires 2 hours of labor and 4 units 4 units of material. Then the company has a maximum, the company has a maximum of 240 hours of labor and 200 units and 200 units of material available per week. Available per week. Then we also talk about the fact that the profit per unit of A is $50. Okay, $50. And for B, it is $40, right? So um the problem, or rather the linear programming problem, the LP problem, can be represented, can be represented as here, maximize. So we want to maximize Z equals 50. We've done this a lot of times, so I'll just go straight 50x plus 40y. And now this is about the profit. We want to maximize the profit, right? Then we have the constraints. So subject to say 3x plus 2y. That's talking about the labor now. 3x plus 2y is less than or equal to 240. So that's the labor constraint. That's the labor constraint. Labor constraint. Okay, as you can see, for labor, right? 240 hours of labor in all. So 2 hours of labor here, 3 hours of labor up there. So 3, 2. And the other one is 2, 4. So subject again to 2x plus 4y less than or equal to 200. And that is material constraint. Material constraint. Okay. Material constraint. Then we still have the x comma y greater than or equal to 0, which is the non-negativity constraint, because we can't have negative labor or negative material. So that's non-negativity constraints. Non-negativity constraints. Okay. So this linear system, this linear system, this linear system can be solved, efficiently, can be solved efficiently using techniques, like the simplex method, the simplex method, or interior point methods, or interior point methods. Okay. However, however, linear programming models, can sometimes fall short. They can sometimes fall short, especially, especially when relationships, especially when relationships between variables, between variables are complex, or involve curves or non-linearities, curves or non-linearities. Okay. Now, let's see those kind of situations. Can we imagine when linear models fall short? So that's like point two now. When linear models fall short, when linear models fall short. So when LP works well, when LP works well for linear relationships, for linear relationships, many real world situations, many real world situations require, oh, sorry, not when, it's while, actually while. So while, okay, while linear programming works well for linear relationships, many real world situations require non-linear modeling, non-linear modeling to capture complex dynamics, to capture complex dynamics. So in that case, LP cannot handle cases where returns, for instance, where returns on investment, diminish or increase non-linearly, non-linearly. So where constraints depend on quadratic or exponential relationships, or where or where problems involve binary or integer constraints, binary or integer constraints that make certain decisions, all or nothing. Okay, all or nothing. So linear programming is just linear all the way. So a very good example will be when we consider a logistics company minimizing travel costs with fuel consumption that increases quadratically as speed increases. So a linear model cannot accurately represent this kind of quadratic relationship. So an LP model would be too simplistic. Similarly, financial portfolio optimization risk, which is often represented by variance, is typically a quadratic function of asset allocation requiring a non-linear approach. Okay. Now let's go to the third point where we talk about non-linear programming because we are basically considering linear programming and non-linear programming. Three, non-linear. Okay, I mean, I've stated it already. NLP is simply non-linear programming, right? So non-linear programming it extends beyond linear linear constraints, extends beyond linear constraints and objective functions. Okay. So allowing for quadratic, exponential, or even more complex relationships, or even more complex relationships. So NLP models, nonlinear programming models, capture the nuances of nonlinear behavior, accommodating accommodating real world complexities, that linear programming cannot. Okay. So NLP techniques, nonlinear programming techniques, are used in fields like engineering, finance, and logistics to address problems to address problems to address problems um that involve interactions or trade-offs not easily represented by linear equations. Okay. Now let's consider an example of NLP. Example of NLP. So suppose a company wants to allocate funds to two different investment options. X and Y with diminishing returns as investment in each increases. Okay. The expected profit function, the expected profit function might be maximize f of x comma y equals 100 square root of x plus 120 square root of y, subject to, so you can already see we have square roots in that place, so that makes it non-linear. So subject to x plus y less than or equal to 200, which is actually, which would represent the total investment constraint. Total investment constraint. Then we also have x comma y greater than or equal to 0, which is non-negativity constraint as usual. Non-negativity constraint. Non-negativity constraints. So now you can see the objective function is definitely quadratic, is definitely non-linear. So I think I should also point that out. Non-linear objective function. Okay, because of the square roots. So here, 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 square root of x and square root of y represent the diminishing returns, which create a non-linear, objective function. So this model cannot be solved using linear programming methods that we know, like simplex, graphical, and all that. Linear programming methods, due to the non-linearity, but can be tackled, with new non-linear programming techniques, like gradient descent, Newton's method, or sequential quadratic programming. Sequential quadratic programming. Okay, so those are methods we can use. Well, we can then conclude. Of course, NLP problems often use iterative methods to find optimal solutions, as closed form solutions are rarely available. In linear programming, right, we have closed form solutions where you can actually say X is this, Y is that. But non-linear problems often use iterative methods to find optimal solutions, as closed form solutions are rarely available for non-linear systems. Some of the most common methods we have said already are gradient descent, and this moves iteratively in the direction of the steepest descent. That's a negative gradient to minimize the function. Newton's method uses second order derivative information. That's a Hessian for faster convergence near optimal points, effective in problems where the function is smooth. And we have sequential quadratic programming, which has been all listed, right? This breaks down nonlinear programming problems into a series of quadratic approximations, solving each iteratively to converge on an optimal solution. So in conclusion, uh, we have seen the differences, right? So in summary, linear programming is ideal. Linear programming is ideal for linear, straightforward problems. For linear, straightforward problems, while nonlinear programming is essential. It is essential for complex scenarios, essential for complex scenarios with nonlinear relationships, with nonlinear relationships. So the choice between linear programming and nonlinear programming ultimately ultimately depends on the nature, ultimately depends on the nature of the relationships within the model, within the model, and the requirements of the optimization task. All right, so that's the end of this. Probably the end of the whole linear programming series, except something else comes up. Okay, so if you have not subscribed to this channel, be sure to do that right away and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know if you want me to teach a topic or solve a problem. Then like and share so that more people can have access to this great content. Till I come your way again, keep optimizing. Bye.